Alright folks, this is going to be the third lecture in my series on algebraic number theory. This is about, we're still working through these preliminaries from commutative algebra, and this is going to be, this one will have a particularly narrow focus. I really just want to prove some proposition about what ideals look like in product rings. Okay, so we have the following proposition. Let A and B be rings with ideals A and B then A times B subset of A cross B is an ideal. Furthermore, every ideal in the product takes this form. That is, they're a product of an ideal in A and an ideal in B. And I can tell you exactly which ones are the prime ideals in the product. The prime ideals in A cross B are those of the form P cross B or A cross P for P, a prime ideal of A or B. Okay, so I want to prove this proposition. I'm not going to prove every detail of the proposition. Some of these pieces are like straightforward exercises in ring theory. Others, so I'll say a couple words about each piece of the proof, but I'm not going to prove every piece in detail. So there are really like three claims here. The first claim is that the product of two ideals, one in A and one in B, is an ideal in the product. Okay, I'm not going to prove this one too much in detail. I'll just say that it's relatively straightforward using the definition. So let A and B be ideals in rings A and B respectively. Then A cross B subset of A cross B is an ideal, as can be easily checked from the definitions. Okay, so if you use the definition of what an ideal is, you can check this thing is closed by outside multiplication and closed by addition fairly quickly. Okay. The second claim is every ideal in A cross B takes this form. I'll say a little bit more about this one. So now let's let I be an ideal in A cross B. I want to write I as a product of an ideal in A and an ideal in B, so I need a candidate for these two ideals that I'm going to take the product of. The candidate can be constructed as follows. Let pi sub A Yeah. Need to erase something. Let pi sub a from a cross b to a, and pi sub b from a cross b to b. These are projection onto the first and second factors respectively. Okay. Then, okay, there are two claims, neither of which I'm going to prove. They can be fairly easily checked using definitions. One is that pi sub a of I and pi sub b of I are ideals in A and B respectively. Okay. This follows from the more general proposition. This follows from the more general result that the image of an ideal under a surjective map is again an ideal. Okay, so pi sub a of I and pi sub b of I are our candidate ideals, and once you have identified these candidate ideals, you can easily check that second claim, I is the product of the projection onto A and the projection onto B. Okay. And like I said, I'm not going to prove either of these two claims. They're fairly straightforward exercises in ring theory. I will, however, prove this third claim, that prime ideals in A cross B are precisely those of the form P cross B or A cross P for P prime of A or B. Okay. So I think I just thought of a possibly different way to prove this using the correspondence theorem, or at least one direction of this. First, let's prove for P subset of A prime ideal. Let's prove that P cross B is prime. Note that by symmetry, A cross P will also be prime when P is a prime ideal in B. Okay, so first let's prove that P cross B is prime, and the idea that you could check this directly just using the definition of a prime ideal. However, there's kind of maybe a slightly slicker argument, which looks like this. Note that we have so we have this surjection pi sub A from A cross B to A, okay, is a surjection. The first isomorphism theorem gives us an isomorphism. Pi sub a bar from A cross B mod the kernel of this map. The kernel of this map is exactly 0 cross B to A. And the I guess you can either call it the fourth isomorphism theorem or our final proposition from last time about the correspondence theorem between ideals of the quotient and ideals of the original ring. We have since P is prime in A, pi sub a bar inverse of P, under this isomorphism, if I trace it back here, A cross B mod 0 cross B is prime. And so the corresponding ideal in A cross B, which is exactly P cross B, is prime as well by the correspondence theorem. Okay, so the idea for the proof of this fact that P cross B is prime is that P corresponds to an ideal in the quotient, and that using, like, for example, this or maybe not this proposition, but this proposition here, using this proposition here, pi star induces a bijection between the prime ideals in the quotient and the prime ideals of A containing A. I think if this proof is confusing to you, I would say just try to prove it directly, and it will maybe be a little bit more straightforward. You can take it, like, you can easily see that this ideal is that this set is an ideal, and to check that it's prime, you just suppose the product of two things are in there, and so on and so forth. I want to talk about the other direction, maybe slightly more interesting. Now we show every prime ideal has that form. Okay. So I'm going to go ahead and let I subset of the product be prime. Since prime ideals have to be proper, either I've got two guys, I sub A, this is going to be pi sub A of I, or I sub B, which is pi sub B of I, are proper ideals in A or B respectively. Without loss of generality, I'm going to assume that it's I sub A. Is proper. Okay, so from here, what do we need to show? We need to show two things. One, we need to show I sub A is prime. And two, we need to show I sub B is the whole thing. Okay. Okay. So, first let's show condition 2. First we show 2. Okay. So we're going to let A be an element of A that's not in I sub A, and we're going to just let B be any element of B. We see that A times 0 times 0 times 0 B. Notice this is going to be 0, 0, so this product is in my ideal I. However, A0 can't be an I, right? Since A is not in I sub A, which is basically the set of all the first coordinates of elements of I. Okay, since I is prime, B is necessarily an I sub B. This element 0b is an I, therefore B is one of the second coordinates of an element in I. Since B and B were arbitrary, this necessarily implies that I sub B equals B. Okay, so there's 2. Now to show 1, we just do this directly. So now we show 1. Let A1 and A2 be an A such that A1 times A2 is in I sub A. We can find, right, okay, we can find B1 and B2. I guess really, sorry. Since A1, A2 is in I sub A, we can find B and B so that this guy A1, A2, B is an I. Note that A1, B times A2, 1. Okay, so I can just factor this as a1b times a2 1 is in this prime ideal I. Thus either a1b or a2 1 is in I. And then either a1 is in I sub a or a2 is in I sub a. This is exactly the definition of what it means to be a prime ideal. So thus I sub a is prime. Since we saw earlier, I guess I didn't really prove it, but I stated it. Since I is I sub a times I sub b, which is, we saw that I sub b is b, and I sub a is prime. This proves the result. So, just to summarize what we've done in this lecture, we've proven this proposition, which says that given two rings A and B, we've completely classified, we've said what ideals look like in the product in terms of ideals of each individual factor, as well as we've identified which of these ideals are prime.